So I'm really excited to be here, and what I'm going to do is I'm going to do my best with all of you just coming back from lunch. I'm going to do my best to make this entertaining, but we are going to get into a couple of topics that I know you want to hear about, but that are a little bit, we get in pretty heavy into the tech. And one of those is security at the edge for IoT. So I know it's on your mind, but so we'll have plenty of time for questions, and if you start to doze off because I'm talking about like public-private key pairs and stuff, that do not snore, or your neighbor will nudge you. Otherwise, we should all be good. So, cool. So my name is Kilton Hopkins, and I'm the lead of an Eclipse project called ioFog. And the gist of it is that we're now running more and more software in the physical world, right on the devices, right where the data is being generated. I want to talk to you today about my clicker not working. Let's start with that. Unplug and replug the USB thing, and I'm just going to use the key on the computer. There we go. So I'm going to talk to you first about why you need to be at the edge, and then I'm going to talk to you about why you want that to be run on open source infrastructure, and then why in particular you might want to use the approach that we've designed. So who knows how long it takes to go to the cloud and back on average? Any ideas of the time measurement to that? Hundreds of milliseconds. 250 milliseconds is what you can typically expect, and that's 1/4 of 1 second. So latencies that you want in advanced manufacturing are usually on the order of microseconds, maybe 20 microseconds. That's like a factor of 1,000 difference, right? So a round trip to the cloud and back is not close. It's not anywhere near what you need for low latency situations. So you have to move the intelligence closer to where the data is if you want that type of performance. So that's the issue with latency. Autonomous vehicles are a very good example. I mean, the processing has to be done in the vehicle. But still, they do make some calls to the cloud and back. So think of a four-way stop. And which vehicle is getting the calculation first that says, okay, we've determined that I'm the first one to go, right, if they arrive at the same time. Far better is to have everything in vehicle. So bandwidth and cost tend to go together. You not only are missing the bandwidth to send all the data that you want to the cloud for processing and back, but also even if you do have the available technological bandwidth, can you bear the cost? So if I'm generating 2 gigabytes of data a day off of a piece of manufacturing equipment, do I really want that heading up into AWS and then being processed there? Because as you know, Amazon's business model is send us your data, it's easy, it's free. Oh, you want to use the data? I'm going to charge you now. So do you really want to be putting it into a place where it's being costing you money? Data corruption and duplication tend to go hand in hand. So let's talk about those 2 gigabytes that were produced on a machine. So has anyone ever done an implementation of a database synchronization across LANs and things like that? So who's dealt with database synchronization before? Would you prefer to keep 2 gigabytes in one place, or do you like making a lot of copies of it? Right? Yeah. So if you have data corruption in the transmission and all of your analysis is done in the cloud, then you're essentially analyzing bad data. And you would prefer to keep it where it is if at all possible. And it's just simpler architecture. That doesn't mean you don't cluster it at the edge, right? You can make backups at the edge and stuff, but why move it out the building if you don't need to? And now some really key points: compliance and security. So when you deal with healthcare information, you have serious compliance issues. So we now have GDPRs in full force here, right? So if you can keep your information in a place where you know you have control over it, then you don't have to certify all the downstream vendors. So there's a lot of advantage to keeping data in the building, in addition to all the other stuff here. And then security. So if you never transmit it, there's a lot fewer opportunities for someone to get a hold of it. And we'll talk about how that works actually at the edge as we go a little farther. So these are kind of, I think even Hewlett-Packard even calls these the 7 reasons for being at the edge, the 7 business reasons for being at the edge. They're commonly stated. There's more nuances than just this. So now, if that's why you want to be at the edge, why do you want your edge to be open source? I'm a huge open source advocate. We've seen a lot of information today about why, but let's talk about why in particular for the edge. And companies are choosing open source for the edge for some really good reasons. So there's community benefits. So it's commonly known if you have open source infrastructure, it tends to be a little bit more tried and true. There's more bugs fixed in that than in something that's proprietary. But now what about the greater community that you're a part of if you're using it? So sometimes proprietary infrastructure is designed for a particular use case, and so maybe a company has customers in oil and gas. So they produce an infrastructure solution that's like edge analytics for oil and gas. And then you're in manufacturing. And you say, okay, well, some of the protocols are the same, right? Modbus is in play, let's use that, and the OPC. And so you put in place the solution, and then you realize, oh, they expect a data rate that's way lower than what I need. And I can't really get them to pay attention to me because I'm not in their key industry. With open source, you tend to have a much broader community across a lot of different industries. And it's auditable. So if any of you, does anybody do anything with blockchain? I know there's a lot of blockchain stuff going on here at the same conference center. Yeah, so in blockchain, do you just take somebody's software that they give you, the binary compiled, and say like, I'll just run this on my laptop and use it as my wallet, right? You need to audit it, and there's reasons, because if you don't see that they're doing things properly, you can't use it. And open source gives you an opportunity to say, well, if I'm running the software on my own hardware at the edge, I get a chance to have a look at how it's done. And so it's often underestimated what you get from having an open source foundation review the technology that you're using. And so then skill sets. So for as much as we pay for engineering, isn't it nice when you don't have to get somebody that's an absolute specialist? If you get an AS400 engineer these days, they cost you a lot of money. The people that have been around for 30 years and know what they're doing, they know how much to charge. You would prefer to have a JavaScript developer, if at all possible, because, well, they're everywhere. I mean, you can go on the street corner in San Francisco and put up a sign that says, need JavaScript developer, and by lunch you will have somebody. So open source brings a greater skill set. People out there are doing a lot of work with, to talk about like web examples, a lot of work with OpenStack, a lot of work with even another good example is just the Apache web server itself, right? We definitely don't want proprietary stuff if we want lower cost talent. And then organizational risk. So what happens if you make your bet on the infrastructure that comes from a startup, and then the startup goes out of business? That's been described already. And then what happens if they get bought, and the company that buys them decides they don't want to give so much for free anymore? And now all of a sudden, the key features that you scaled on are the features they want to charge you on. And this is a pretty bad thing. And then licenses. So this is not often discussed very much. There is a lot of stuff out there that you can buy and buy a license to embed into your product, but is that license really commercially friendly? And the EPL 2.0, so the Eclipse Public License 2.0, one of my favorite licenses, you actually can use it commercially in a lot of ways that other licenses don't let you. So think about if the open source technology is what's making your product kind of advance into the new world, or making your IoT product possible, are you absolutely sure that what you're using will allow you to release that product commercially and still do what you want to do? So, also, you own the infrastructure. So now this is kind of an edge particular reason for using open source. So if you take, I'm going to make fun of AWS IoT a lot. I love Amazon, I love AWS, but there's a lot of reasons that I don't like AWS IoT as an IoT platform. If you take their SDK and you put it, which is proprietary, and you put it into your hardware, so your device that you're then going to sell, and they decide to change things, you are essentially selling a product on Amazon's behalf because their technology is not open for you to modify or fork. You can't even set it up to talk to your servers. It all talks to their servers, so you're beholden to them. Own your infrastructure, because whatever business you're currently in, if you're a lumber company manufacturing specialty lumber products, you don't want to now become a lumber company that sold all of its data to some cloud company. You still want to own your business. So if you make your products smart in any way, own the infrastructure that makes them smart. And you want to own the data. So data is actually like the new currency. There's a lot of cities that are now realizing that their data is becoming one of their fastest growing assets. It used to be their infrastructure, their roads, their bridges, their pipelines, and now their data is equally important. So you definitely want to keep hold of that. And an ecosystem focus. So walled gardens seemed like a good idea in 2014 for IoT. The Nest is still trying. You guys know Nest, right? Who has a Nest thermostat in their home, by the way? I don't actually. I just had to raise my hand so that you guys would raise your hands. So Nest is one of those companies that believes that they should have products that are pre-certified to work with them, and everybody else kind of please stay out. This is our walled garden, right? Might be okay for consumer products. It definitely doesn't work in industrial IoT. And then enterprise integration, you're going to want stuff to work with your backend. So legacy is as important for IoT as it ever has been for any other enterprise scale project. For consumer stuff, maybe not that important, but I sincerely doubt that a hospital is going to replace their MRI machines because they don't work with their IoT gateway that they bought. More likely the other way around. So you really want your edge stuff to integrate with legacy, and unfortunately, the architectural approach I'm going to show you is very legacy friendly. Cool. So what on earth is Eclipse ioFog? It is a complete edge computing infrastructure foundation, and in this case, foundation means base layer, not like foundational open source organization. That's Eclipse. Okay. So we're going to do a version release at the end of October, and we're going to actually have a change at that point. We should have a change to all of the code being moved under github.com/Eclipse. That should happen. So today you can get it at github.com/ioFog. And so we've got this new destination site coming up, iofog.org, that will basically be like, one click to get started so that you can try the whole thing out on your laptop. So you can take it on the plane even and do some edge computing right there. But this still doesn't say anything about what it is. I should probably go back a slide and talk about this for a moment. So if you want to run software in the physical world, there's a couple different ways you can do it. You can either embed that software into the board, so commonly known as either firmware or a binary that's been distributed along with the OS. So if your little device runs no operating system or runs FreeRTOS, you're probably going to use a firmware-based approach to run software in it. These devices are actually, I'll show you a topology here in my presentation, these devices are below the level where we typically come in. When you need to add some intelligence to kind of aggregate data from multiple devices and stuff, now you tend to be on that gateway layer. And it was mentioned earlier, I think in Ben's presentation, about like kind of the three layers. You've got these small devices, constrained devices, you've got gateways, and then you've got cloud layer. That gateway layer is the magic where the intelligence across many devices starts to occur. It's typically where you would do pure edge computing. And so anything that runs Linux can run Eclipse ioFog. And the goal is to shift away from knowing ahead of time what software you want to put out in the world and be able to do it dynamically after the fact. So if I put an IoT gateway in my car and I use the firmware-based approach, right, or the embedded approach, I need to think ahead, like, what do I want this thing to do? Oh, talk to Bluetooth devices in the car, okay, and you start to write some code. But if you use the ioFog approach, you just put ioFog in the gateway, put it in your car, drive away, and then later from your desk at work, you decide to write and deploy a new application. You write it, you use, I'll talk about the tool sets used. You hit push, and it shows up in your car and starts running, and you can change everything like that dynamically. So that's the gist of what it is. It's about running software in the physical world. Okay, so there are a couple of components to it that are in Eclipse ioFog. The first thing is called the ioFog agent. This is a tiny install. Tiny means 15 megabytes. So again, not for like Arduino-based devices, right? This is for things that actually run an operating system. Like Yocto Linux is fine, but even Red Hat, all the way up to Red Hat is good. And this agent software turns the hardware into edge computing. It's as simple as that. You put it in and you're done. And then there's this part, this control plane for it. How do you manage all of it? This thing's called the fog controller. Here's where we depart from the architectures that are currently usually in place for any kind of edge intelligence or edge computing or fog computing. Most other architectures have some kind of a cloud that controls what's happening at the edge, and the two are married together. The fog controller is yours. You can put it in your own cloud, you can put it on your own LAN, you can put it in the very vehicle where the edge computing is taking place. The control plane is distributed wherever you want to put it. And in an upcoming release that'll happen in 2019, it's completely decentralized too, meaning that basically if you can talk to any part of ioFog, then it will get the messages to the rest of them as far as the control plane. But for right now, fog controller, the control plane is this thing that you install on your systems. And then how everything talks together, there is an optional piece called ComSat. So these three pieces together are your main infrastructure. You've got the thing that's doing the edge computing on the device, the thing that gives everybody their commands, and that's like your management system, and then this additional piece that lets them all talk together on a software network. So as things start to converge, they'll all essentially become one piece of software, but until they do, you've got these three separate pieces. Allows you some good scale. And then you've got SDKs for how to build. One important thing to note about Eclipse ioFog is the SDKs are optional. Everything that you do to build software for the edge is exactly how you would build it for the cloud. So the SDKs are there to give you a little leg up. They're usually only a couple hundred lines of code each. And that's because they basically make your API calls for you. The APIs that you use at the edge with ioFog are REST APIs that are on local loopbacks, so they're very fast. And even faster is WebSockets that you use for real-time or near real-time data transmission. So we like to say, if you have the skill set to build anything for the cloud, you have the skill set to build it for the edge. And then we've got some example edge microservices. Here comes a slide you'll probably want to take pictures of. I've noticed the architecture slides get a lot of photos. And that's good, because that's like, you need a diagram. This is the structure of what makes edge computing possible with Eclipse ioFog. At the very bottom, we have what we call an edge kernel. You probably should rename that because it rides on top of the Linux kernel, but we call it an edge kernel because it's the underlying thing that talks to the hardware and abstracts some stuff. So down here is where you get your hardware security monitoring, hardware health monitoring, and some abstraction of the hardware. And then this is where you can implement secure device connectivity. So if you need to do encrypted data over Bluetooth, then you would work here to put in place some of those layers. And then there's also resource management. I don't think I have a slide that shows the resource management. So think about this. You've deployed IoT gateway hardware, and you've deployed it on 100 oil pumps. And these oil pumps are all about 400 miles from the nearest person. So it's very expensive to get out there and make changes. You would love to run some analysis there at the oil pumps where the data is coming at a rate of 50 kilohertz. So in other words, about twice, if not more than twice the bit rate needed to do full-time streaming audio. You don't have any connectivity out there except a cellular plan that you're willing to pay for. So you need to, in other words, put the software right there at the oil pumps. You try to put it out there, but which of the pumps have enough CPU and RAM available right now to do your processing? You would like to know that. This is an example of resource management. Once you put things out in the world, what condition are they in? Can they fit another piece of software right now? Should I run it later when this other job finishes? That's all that I mean by resource management. The layer above that is where we get into some of the magic of making it easy to build for the edge. We call them fog services. So who's used S3 buckets, S3 on Amazon Web Services? Has anybody used S3 on AWS? Yeah, cool. So some of the magic of S3 is never again do you have to worry about how am I going to store, do simple data storage here in the cloud. It's just done for you. So if anyone on your team is rewriting that functionality, you'll give them a slap on the wrist, don't need to do that, it's been done. Same thing for edge computing. Nobody should have to worry about some of these simple, run-of-the-mill tasks. And one of them is how do I distribute data from one point to another? That's all done for you. And so that's where the APIs sit that you're going to want to work with. And above that is the most exciting layer, which is how do we run applications at the edge? For us, applications are microservices, and they can also be a technology called unikernels, which is even smaller. But for the most part, just think Docker containers. So this is an important show of hands. Who has heard of Docker? Okay, good, good, good. It should be a good number of hands. Docker containers work naturally with Eclipse ioFog. So if you can package something in a Docker container, you can run it with ioFog. And this is all how do you start up and shut down stuff and you know, what version microservices are running where. And what do you want to do? Often you want to take data from something. Get data off of a sensor. Maybe it's a sensor that's talking over Wi-Fi, maybe it's talking over Bluetooth or LoRaWAN or whatever. You've got some kind of data coming in. How about using a dynamic piece of software at the edge to collect the data? Instead of having to have the device be aware of where to send the data, you could then have the gateway become dynamically intelligent. Or you want to do some analysis and use some business logic. The most exciting stuff, which I'll be doing a demonstration tomorrow and the next day, that'll be running at my booth that you can stop by, and you can actually see image recognition happening right in the room. There's no cloud connection, but this thing is way smarter than your Google Cloud image recognition and so on. It's all happening right there, right at the stand. So machine learning and AI stuff at the edge is really important. It's a great way to turn a gigabyte of data into 200 bytes of textual output. So why would you use Eclipse ioFog and what are companies doing with it? So, there's a slide that should have been earlier. This is what we do. We make it possible to run any software in any given physical space on the planet and to do it securely and have remote control the same way you do for cloud and data center. And we make it as easy to build for the edge as it is to build for the cloud. So here's an example of something that's important to one of our customers. We're going to talk through the use case here. This is a smart agriculture use case. As you can see, there's a cell tower there. It just so happens that this customer makes cell towers. And so they're able to put the edge computing right there where the LTE transmissions are being received and rebroadcast. So here they've got drones, they've got a tractor, and so on and so forth. So managing the location of data, which is the process is called data provenance. Where was it generated? Where did it go? Where was it stored? Where was it copied? Where was it backed up? And if you don't know this, then compliance goes out the window, because it's really hard to guarantee compliance for something when you don't know where it is. So data provenance can be very expensive. So one of the things that we do in this use case is, how do you know that data is remaining within a physical boundary? Well, if you know the location of the things that are doing the edge computing, and you have full control over what data moves from what point to another, and you put those two things together, and you can start to enforce physical rules. We have a customer that basically just draws a line on the map around the factories where the data needs to stay, and then adds rules. And one rule is no data leaves. Another rule is no data enters. You set these policies, and then as long as the whole system is using Eclipse ioFog, it guarantees that the data never leaves the factory. And then you can certify to your customer, yes, when you use this equipment, we can guarantee you that none of your operating data is leaving your four walls. This is really important. How about what to do with a rogue node, something that's been compromised? So we've got a little X down here with the ninja face. So up until now, if you add hardware into the world, you're massively increasing your attack surface. Basically, everything you put out there that talks to your back end is a potential hacking point. So let's flip that upside down. With Eclipse ioFog, every node that you put out in the world increases your defense surface. So if the way that everything's interconnected is by working together, and the software is built to check each other, it's very fast to sniff out a bad actor. So this is a little bit inspired by the architecture of blockchain. Blockchain is a peer-to-peer network, and each peer is responsible for validating other peers in very simple, inexpensive ways. Makes it really expensive to be bad, and really inexpensive to be good or to check whether something's good. Same philosophy. So nodes in the ioFog network, so in other words, you've rolled out your fog, right? You've rolled out your edge computing. The nodes check each other in a way that when something smells bad, it never reaches some cloud, it never reaches your back end. It gets cut off as soon as possible. We'll talk a little bit about how that's done with this. So these are, and feel free to argue with me on these, but these are the 8 requirements for secure commercial grade edge computing. So first you have to trust the hardware. It doesn't do a lot of good if you buy a compute board that doesn't allow you to certify that that board is still intact, right? So this is called hardware root of trust, and some of the technologies around it are like Trust Zone or TPM 2.0. It's all good. And there's a lot of new stuff that's coming out, like USB modules that once you plug them in, they learn from the rest of the system how to make their key, and then if you take them out, they change the keys, so you have to keep it plugged in the whole time. Either way, it doesn't matter how you do it. How do I know that the hardware is the hardware that it's supposed to be? And then you need to know that the software is pure. So who uses iPhone versus Android? iPhone users in the crowd? Yes, that's good. There should be about half. So you can get apps from the Apple App Store, and they're going to run on your iPhone. If you attempt to jailbreak your iPhone to run apps that are not certified by Apple, you can find ways to do that, but then you no longer know that the software that you're getting is pure. Right? It doesn't pass the review process and all this stuff. So know that the software that you're pushing out to your edge computing resources is pure. And one of the best ways to do that is to just have like a signed microservice, right? And then that'll work with your guaranteed hardware. And then know what software is running on what hardware. So in a factory situation, if I have a microservice for the edge that is looking at which employees are using the specialized equipment, and it's supposed to be just the ones that are trained to use it, right? So we detect the employee badges, and we can maybe do that with Bluetooth, or we can do that with NFC, where they have to tap to sign in, right, to use the expensive machinery. If the microservice that you wrote to do this ends up running like in the men's bathroom or in the cafeteria space, it's no good. So you need guarantees that the right software is running on the right hardware, and that's the next step. And then let's talk a minute about delivery of secure and secret information. So if I write some software to run at the edge, and it's going to gather data from how about a temperature sensor? And it's going to report that into my AWS cloud. That's fine, nothing wrong with it. So I need an API key in order to be able to report the data in the cloud. I need some credentials in order to be able to tap into the cloud backend. If you bake that into the code, then now if anyone gets a hold of the software, they also get a hold of your backend. You would prefer to deliver that information once you know the software is running on the right hardware, that the software has not been compromised, and the hardware has not been compromised. This is like a stack. We're building as we go, right? So with Eclipse ioFog, you get to deliver your secret information after the guaranteed runtime is in place. You know the prior three, that's when the secret will be delivered. Great way to send an API key. Okay, and you need total control over the data flow. So all of this is good until you realize that the microservice you deployed, some programmer accidentally left the logging system in place, and it reports out all of the sensor data to their home PC, which they're using for debugging. This is bad. Eclipse ioFog will actually keep track of what's happening on the hardware and say, there's only supposed to be one open network port, and yet we have 5 other open ones. So we're not going to shut this thing down, but we're going to put it into quarantine, which that's actually one of the next points is, that's the next point, automated quarantine. We're going to put this node in quarantine and stop sending any data, and everything's on hold until you can review it. But we've detected something doesn't look right. And this is what you need for total control over data flow. And in addition, if you don't authorize data to move from one point to another, it can't move from one point to another. And that's really important. So otherwise, you wouldn't be able to do that thing where you guarantee the customer that the data stays on their site. You need a guaranteed shutdown and wipe of all data and edge microservices. When I decide that it's time to stop running that proprietary AI that we wrote for the edge, the thing that makes us all our money, and I want to turn it off right now because that bus is going to go out of service or whatever we want to do, you need to know for sure that it shuts down and wipes, and that's part of Eclipse ioFog. And last but not least, all this is great until you realize that if somebody jailbreaks it, that the whole thing falls apart. You can never stop jailbreaking. People will find ways to hack your software and your products. But at least you can become aware that something doesn't look right because something has changed. And in that scenario, you can decide what you'd like to do with that piece of hardware, that edge compute node. You can say, it looks like it may be jailbroken, cut it off. Or, all we're getting is moisture data from the crops. We can stand it if somebody's trying to send us bad data, but the data looks fine, let it go. So those are the requirements. How are we doing on time? Yeah, I think we've, actually, maybe we need to speed up a little. Okay, so architectural principles. So in designing edge computing infrastructure, what is important? You guys are doing great after lunch, keeping up with this. So first, be protocol agnostic. MQTT is one of my favorite protocols. You can use it with ioFog, but you can also use other stuff too. And that's because it's already above TCP/IP, and what you're doing there is you're passing whatever bytes you want. You can pass video, and then you just got to label it. So stay protocol agnostic, one of our principles, and it's fully distributed. I mentioned you put the control plane on your own servers, your own hardware, your own gateway box. It doesn't do any good if you're using open source, but you're tied to a vendor, right? So you need to be able to put it wherever you want. Be backend agnostic. And that's because today you decided to prototype with AWS, but tomorrow you sign a contract with Microsoft Azure in order to be your vendor for all of your high-scale backend. You should be able to switch, and also you could just use your own stuff. It doesn't have to be some cloud system. Full control over data flow, we already talked about that. And now hardware agnostic. ARM or x86 doesn't matter, and whatever comes out, if anything, any other architectures emerge that are important, we'll adapt to them too. The whole idea is that you want to choose commodity hardware. You can choose expensive stuff, but there are some companies doing edge computing where everything works as long as you buy their box. And their boxes are surprisingly expensive because that's part of their model. If you want to choose a $200 edge compute node, a $60 edge compute node, a $10 edge compute node, or a $6,000 one, it shouldn't matter. And yes, it does. Eclipse ioFog runs on $5 edge compute nodes. So you can make some really interesting use cases if the compute hardware doesn't have to be that heavy. And that's essentially what's changing in IoT is, or one of the reasons that IoT is on the rise is the cost of putting computing into physical products is very, very low compared to how expensive it was like 15 years ago. And so if it's inexpensive to have something with 1 gig of RAM and a dual core 64-bit processor or quad core, and that costs like $10, which is, well, I think the 512 megs of RAM for the Raspberry Pi Zero, but things are so inexpensive now that if you can choose cheap stuff, why wouldn't you want to? Development for the edge is easy as for the cloud. Again, just don't want any new skill sets required. And be OS agnostic. We're not there yet. We currently only run on Linux, but we're moving toward other models. The question is, how do you do edge computing on an iOS smartphone, on an Android smartphone without needing to install or jailbreak the Linux there. So we're working on it, but right now Linux is the dominant operating system for IoT systems, and it's very prominent on smart devices too, so it works. We like to use software to overcome hardware issues. And what I mean by that is, if today you're using a special Bluetooth receiver to get the signals for patients in a hospital, and you really would like to do more with the data, but the company that makes the Bluetooth receiver box doesn't offer anything like that, you're kind of stuck putting all of that patient data into the cloud. With Eclipse ioFog, you can put it on, let's say, a Raspberry Pi, which is $35 US, and that's capable of now doing the Bluetooth communication. So then the software that you want to run, you would use that to talk to the devices and overcome the fact that this is not a Bluetooth gateway. You can make it one by putting an edge microservice in there. So anywhere there's a Bluetooth radio, you can do the same thing you did with specialty hardware before. So by using software to overcome hardware problems, you think in terms of microservices, not in terms of boxes you need to buy. And then finally, make connectivity truly commoditized. I'm all for connectivity companies remaining in place and doing well and profiting financially. It's just, if connectivity is the driver of data access, then we've still got a problem. What I mean by that is, right now, being on the network is a big portion of getting access to data. It shouldn't be. I should be able to be on the network where sensitive data is and still have no chance of getting it if I haven't been authorized. And so to that order, you should be able to use cellular mixed with satellite, mixed with a wired LAN, mixed with fiber, internet connectivity to your factory. None of it should matter anymore. However you get connected should be just the thing you do to bring your edge computing online, but it shouldn't be the driver of whether these devices can see each other and share data. That should all come via a software network that runs over it. So connectivity becomes a little bit more like water. All water is the same if it's clean, right? It'll be suitable for the purpose. And being on the network isn't the way that you get access to data, it's being part of an authorized group. So it's a security-oriented approach. So let's take a look at this fake company, which is called Smart Tools 4.0. It's obviously German. So for this company, using ioFog, tools know which employees are using them, and they can use this to improve the proper safe usage, provide training, and increase efficiency. Remember I said the microservice knows that the trained employees are the ones using the really expensive, really dangerous equipment. Tools know on which jobs they're being used. This is actually a really good market opportunity for this company that makes the tools, because knowing on which jobs they're used allows them to say, did you know you use our tools 40% of the time on jobs that they're not suited for, but we have a better product that will last longer, and we're happy to sell that to you for a discount if you'll switch today, that type of thing. Or you could just do software as a service or data as a service and so on. Track the location of tools and parts. That's asset tracking is like a key use case for a lot of IoT situations. And sense tool usage behavior and components. So you're not using it right, the angle is off, the vibration level is too high, and so on and so forth. So basically, add smartness to the tools that they already sell. And here's what the topology looks like in the environment where they're implementing ioFog. This topology is generalized also enough for you to apply it to most situations. So we all know the cloud. That part doesn't need much explanation. And clouds are part of our lives. They won't go away. You need to just use them properly. And all the way at the bottom is this constrained device layer. These devices tend to run firmware or an RTOS. Occasionally they run an operating system like Linux or embedded Linux, but most of the time they're really, really dumb. And you want them to be dumb, because if the device costs you $10 and it could have cost you $1, you'd prefer a lot more of the $1 devices. So the part that we need to really talk about is the in-between. If you take the cloud and you bring it on-premise, we call that a micro data center. So on-premise solutions have been around for a while. Typically, though, you connect them all via VPNs. We're advocates for no longer using VPNs. They're incredibly dangerous for IoT systems. Not saying don't use VPNs in general, just don't use them as the way you move IoT data from one location to another. You don't need to. But so the micro data center is very cloud brought to your physical building. The orange layer highlighted is the magic. Something has to be really close to the stuff that's generating the data. So who knows the range for Bluetooth 4? How far does it go in meters? Yes, 10 meters. So if you've got a telco closet in the back of your factory, which has got your micro data center, which has got your on-premise solution from HP or whatever, can that talk Bluetooth to devices that are about, I don't know, almost half a kilometer down the factory? Cannot. Something has to be right there. This orange layer is what I call the farthest reaches of the edge. This is where edge computing is the hardest, and that's what we focused on. Because if you can do it here, it's really easy to do it at the micro data center and really easy to do it in the cloud. And what matters here is this is the inflection point between low power wireless, things like LoRaWAN and Bluetooth Low Energy or Zigbee, and the TCP/IP that we're accustomed to. And the hardware that sits right here is typically called an IoT gateway. And so this is where the edge computing matters the most. This is where the magic happens. This is the first place in the topology that you can aggregate data. Because a temperature sensor that costs $5 should not be doing all of the AI processing for all the other temperature sensors. Those are its siblings. So its parent in the topology is where the aggregate processing should happen. And this might sound, let me see if I explain this right. This is your last chance to add context before you lose the resolution of the data and lose the context. If I take a temperature reading over Bluetooth Low Energy, I'm probably going to want to keep it to the minimal data that I need to transmit. So a temperature reading might be 4 bytes if it's high precision. If I add a timestamp to that, that's another 4 bytes. So I'm doubling the amount of data I need to transmit just to add a timestamp. Plus, if anyone's done an IoT deploy, you know what else is a problem. You have to synchronize the time on every single sensor. Don't add the timestamp one layer up at the magic layer, right, of the edge computing. That's the right place to do it. It's also the right place to put unique IDs. So their business requirements, and I think regarding time, we'll just, oh yeah, we've still got some time. I'll wrap it up quick. Principles for them: data can't leave the factory. Manufacturing workflow information comes from SAP on-premise. So in other words, that mandates edge computing right there. If you have to talk to some on-premise resource, such as like an in-factory SAP system, or in a vehicle, some command and control that's happening in the vehicle, you already need to use edge computing. The smart tools must install their own non-data management network. Or smart tools, a company, they must install their own network. Oh, that's, yeah. The customers told them, you can't use our connectivity. You can't use our network. So if you've got any kind of like remote update for the smart tools you sold us, you got to install your own network. So that was a driver for edge computing. Analytics must be produced on site. And the security model must prevent endangering employees in the facilities. The customer needs to install it themselves. Edge computing is also something that helps solve our situation of setup and deploy, because you can add more intelligence there, and that way you don't need to do so much configuration. Let's see, edge microservices must be commercializable, so they can be able to sell them, and remote management at scale. Diverse hardware options for their edge compute, so buy commodity stuff. And finally, they needed, or almost finally, they needed to provide APIs for their other vendors, and they needed to manage this system across different customers at scale. So those are the reasons why the company's name has been masked, Smart Tools 4.0 GmbH, but these are all the things the company needed to accomplish, and so edge computing was their only solution, and so they started working with us. It was pretty cool. One more diagram for you, and that's my last slide. So in the smart agriculture situation, the LTE base station has backhaul to the internet. It runs ioFog, because then you can run microservices at the LTE base station. The cloud, though, also runs ioFog, taking advantage of the secure peer-to-peer mesh network that is, between the fog nodes. And then all of the things out there are running ioFog, but the devices, the sensors that are like on the tractor, on the drone, whatever, those are not necessarily you running ioFog because they're too small. So you could think of these things, as each of these is kind of like a gateway. They all have sufficient power and so on. So that's kind of the end topology for that use case for the smart agriculture. I know I only left about 10 minutes for questions or less. I left 15. I think it works out. Okay, great. Cool. How much? I have 5 minutes. I'm sorry. Okay, quick questions, and I promise I'll be around to answer more stuff afterwards. So that's it so far. Yes, question back there. And what are we doing with, should I walk up and, you have another one? Oh, okay, great. Oh, gotcha. Cool. Thanks, Ben.
Thank you. I have a different use case, a use case like autonomous driving, right, which also requires edge computing. Does a network like a mesh network add both size and latency to it? And if yes, is it linear decrease or is it more prominent?
So when you say mesh network, you're talking about the mesh that I mentioned, right? Yes. So there's a big difference between mesh networks that are used for reliability. Things like Zigbee, is a wireless technology that allows for mesh networking, and Bluetooth 5 has mesh networking. These meshes are there to make sure that there's always a partner to hop through. The mesh network that is the software mesh network that comes out of ioFog is a managed one, meaning that it's optimized for segmenting and things like that. It is not a pure mesh in that every node talks to every node, because the concern that you're bringing up is pure mesh networks where every node talks to every other node, they get really expensive in terms of the bandwidth or in terms of the power consumption, but it's still a mesh. It's a mesh that is there to make sure that you have partners in processing and peers to check your work and a path through. But two parts that never need to talk are never actually connected. Yep. So yeah, we try to minimize the overhead, and the mesh is an intentional mesh for the way it's designed. Cool. Other questions? Yes, you can just take this from me.
So when do you think that the need to store some metadata for some of the measurements that you get is the requirement to keep it disappears? So I'm thinking about every sensor has a degree of accuracy, for instance, and over time you might be able to improve the analysis that you create on the basis of those measurements. But obviously you don't want to store those measurements forever either. So what are your thoughts on that?
That's actually a really good, interesting question. So if you have edge storage that is in the order of, say like 1 terabyte on an IoT gateway, I think it's feasible to store a lot of metadata there and then mine it later if you want some information about it. You don't need to transmit it up. If your storage is limited to something like 100 megabytes, right, or even 1 or 2 gigabytes, you might want to consider either summarizing it and sending it upstream, or doing like, when there's not much happening in the factory, like over a weekend, you could push some edge software in to do the analysis and move out the results or something. But it's the point you're bringing up, which I think is really important to note, is a lot of information, when it's gone, it's gone. So if you don't store it for later usage in some way or move it off-site, when you want to know, well, geez, how many decimal places were we reading at the time? And is that really is the degree of accuracy able to be improved? You won't know it if you never recorded it and kept. So, but then you can't keep everything, because if you do, you run out of space. So edge storage is getting cheaper and cheaper and easier to implement. So if you can, have your IoT gateway capable of storing more, because you might want it. Yes.
Hi. Yeah, I would like to ask the question of the security implementation. Yeah. So does it mean that every part you will have different type of security solution that you need to implement? Thank you.
If you're talking about the network connectivity that comes from each of the portions of the solution, you definitely want to choose your method of connectivity having some security implementation. Otherwise, you're only transmitting now encrypted data over an insecure wire. So in that case, your packets of data are encrypted from one ioFog point to another. But why would you want to have an insecure network connection? Cellular is a good option. LoRaWAN is a good option, right? But there are a lot of radio technologies, think of old SCADA systems, that have the data is fully exposed. And if your first point of contact between the device and your IoT gateway is insecure, then you can't guarantee that you started from a secure place. So choose connectivity options that allow some model of security that you trust. And once it touches the ioFog part, we have point-to-point encryption, but you still would want to put that over something that has your basic, SSL and so on. You just wouldn't want to choose anything weaker. But the simplified version of this is you no longer need to figure out your own security up after a certain point. Once you hit the ioFog point, you don't need to say, geez, if only I had a solution that would verify the hardware on the cellular network for me. We got that. We can help you with that. Yeah. Yes.
Recently, we have migrated all our software services in the GCP, the Google Cloud Platform. And we are basically developing some sort of IoT services for our healthcare services in rural and urban areas. As you mentioned, you have services, all the other cloud services provider. So how does it fit for the Google services?
Yeah, so the Google stuff works just like any other backend. You have a chain of microservices, and in this case, I'll walk it through in this topology. First microservice here, connect the data, maybe summarize it or do some analytics. maybe here you have a microservice that takes the data from all of the different machinery. And then there's 4 microservices in each box to illustrate that it's numerous. You have n number. The last microservice in the chain is probably a microservice that is built to talk to your Google Cloud. And so you do a handoff. And so it's very typical to have first microservice is something specific to the device, right? It speaks the particular command set for this device on a serial port. Then business logic, business logic, business logic. Last microservice is backend specific. It knows how to talk to AWS Kinesis. It knows how to talk to the Google Cloud for the IoT data ingestion. Or it drops it into an InfluxDB instance or something. Yeah, so that's how you do it, is use one microservice or more to do your handoff to your backend, and that's how we allow kind of any backend integration. Nothing hard-coded, yep. And build it in any language, by the way. So if you've got it already written in Node.js, pack, push, done. Yep.
Last question. All right, last
All right.
one.
Do you have any partner companies that you work with to deliver solutions to your customers?
Yes, we do. We have partner companies in all kinds of different verticals, and in even some that are larger, like companies like Cognizant and so on, are starting to look into getting trained up on ioFog. What we like from partner companies is if you make hardware that would be good edge computing hardware, it's a kind of a piece of cake to talk about embedding, right? And there's a smart camera company that we work with in Boulder, Colorado, back in the States, that does GPU-enabled cameras. And so putting ioFog in the cameras means customer buys a camera, now they decide to build software. A really good partner for us would also be like a system integrator company that says, well, I want to spread across maybe these 5 industries, healthcare, and then hospitality, and then smart buildings or whatever. And they have a special set of skills. They know what sensor to use. They know how to manage the data. And they'd be a great partner because they can learn how to use ioFog and then train their development team. And basically, we could just keep them apprised of how they would want to do certain stuff. Like, here's a reference architecture. Here's a reference approach for this or that. But my company and in general my care over the Eclipse ioFog project is oriented around serving the best interest of everybody, no matter what they use it for. And so industry-specific knowledge is not something that we have, and that's what partners are really good for. Cool. All right, thank you. Cool. Thanks.